The F-14 Tomcat, one of the most iconic aircraft in aviation history, was designed to perform a singular high-stakes mission, intercepting supersonic Soviet bombers before they could launch long-range missiles capable of crippling the US Navy's largest aircraft carriers. This mission came at a time when the US military had nothing in its arsenal that could handle such a threat, and thus the F-14 was born. It was a technological leap forward, bringing together speed, versatility, strength, and firepower in one stunning package. The need for the F-14. During the Cold War, the Soviet Union was developing increasingly sophisticated long-range bombers capable of carrying nuclear missiles. These bombers, with speeds faster than most aircraft of the time, could reach American naval fleets and destroy them from long distances before they could be intercepted. The US Navy needed a fighter aircraft that could fly at speeds of Mach 2 or more to intercept these bombers at high altitudes. Additionally, the new aircraft would have to be versatile enough to engage slower, more agile enemy fighters when necessary, and strong enough to withstand the harsh conditions of carrier-based operations. Thus, the F-14 was designed to be the perfect solution to this high-risk scenario. The Swing Wing, a shape-shifting aircraft. The F-14 had one key feature that set it apart from all other aircraft of its time: its variable sweep wing design, also known as the Swing Wing. This system allowed the aircraft's wings to change their angle during flight, adapting to different speeds and missions. At lower speeds, a higher wing sweep was ideal for generating lift, especially during landing or takeoff. As the aircraft reached supersonic speeds, the wings could retract, decreasing drag and allowing the aircraft to maintain high-speed flight. This made the F-14 the ultimate versatile fighter, capable of both slow-speed dogfights and high-speed interception. While the concept of variable sweep wings wasn't new, the Germans had experimented with this idea during World War II with the Messerschmitt P1101. It wasn't until decades later that the technology was ready for practical use. The Messerschmitt design, though groundbreaking, never saw production. However, it laid the groundwork for future innovations, and years later, the Bell X-5 aircraft, inspired by this concept, would prove that the idea had potential. Titanium engineering at its best. A crucial component in the F-14's swing wing system was the aircraft's wing box. This vital part of the structure is essentially the foundation of the entire aircraft. It connects the two wings and supports the aircraft's weight while also allowing the wings to pivot. Due to the stresses placed on the wing box, especially with the added complexity of the variable sweep wings, engineers needed to make it as strong as possible while also keeping it lightweight. The solution came in the form of titanium, a material known for its excellent strength-to-weight ratio. Manufacturing titanium is notoriously difficult and expensive, but Grumman, the company behind the F-14, developed a groundbreaking process called electron beam welding to make it possible. This process involves using a beam of high-speed electrons to generate heat and join titanium components in a vacuum environment to avoid contamination. The titanium wing box reduced weight by around 15% compared to aluminum alternatives, providing the necessary strength while keeping the aircraft's weight manageable. Engine complexity and challenges. To achieve the speed and power necessary for Mach 2.3 flight, the F-14 required extremely powerful engines. Grumman chose to equip the F-14 with the TF-30 engine, which had been developed for the F-111 and F-4 Phantom aircraft. While the TF-30 was capable of providing sufficient thrust, it was not without its drawbacks, particularly when it came to maneuverability. The engine was highly susceptible to compressor stalls, a condition in which the airflow through the engine becomes disrupted, causing it to lose power and potentially flame out. One of the most tragic incidents involving the TF-30 engine was the death of Lieutenant Kara Hultgreen, the first female US Navy fighter pilot to die in combat. During an approach to land on the USS Abraham Lincoln, a compressor stall caused by a yaw in the aircraft led to the tragic loss of control. This incident highlighted the engine's limitations and the dangers it posed during high-performance maneuvers. In 1984, the F-14 was upgraded to use the more powerful and reliable F-110 engine, which was specifically designed for fighter aircraft. The F-110 offered a significant improvement in performance, with 32% more thrust, better fuel efficiency, and a greater tolerance for high-G maneuvers. The new engine allowed the F-14 to perform better in combat and stay in the air for longer periods, making the aircraft more capable and less prone to failure. A game-changer in air-to-air combat. The F-14's radar and missile systems were state-of-the-art, with the aircraft capable of carrying 6 Phoenix missiles, one of the most advanced advanced air-to-air missiles ever created. The Phoenix missile was designed to take down high-speed bombers from long distances, and it worked in conjunction with the F-14's powerful radar system. The AWG-9 radar, which was 10 times more powerful than the F-4 Phantom's radar, could track 24 individual targets at once, allowing the F-14 to guide its missiles to multiple targets simultaneously. The Phoenix missile, once launched, could accelerate to Mach 5 and climb into the stratosphere to reach its target. It was capable of making extreme turns of up to 17 Gs, a maneuver that no fighter aircraft could match. However, the Phoenix missile's potential was never fully realized, as the Cold War scenario for which it was designed never materialized. The missile was expensive and rarely used in combat situations, but it represented a significant leap in missile technology. A high-stakes operation, landing and taking off from an aircraft carrier is no small feat, especially for a fighter as heavy and complex as the F-14. When landing, the aircraft relied on its arresting hook, which would catch the arresting wire on the carrier's deck to bring the plane to a rapid stop. This process was not always smooth, and in 2002, an F-14's arresting hook broke off during landing, causing the aircraft to dip below the deck with afterburners on. Fortunately, both the pilot and radar intercept officer ejected safely. Taking off from an aircraft carrier is an equally exhilarating experience. The F-14 would be launched via a steam-powered catapult system, or in more modern cases, an electromagnetic rail system, which could accelerate the aircraft to 290 kilometers per hour in just 2 seconds. The pilot would release a switch to kneel the aircraft, lowering the nose gear and preparing it for takeoff. The F-14's wings, positioned at the front of the aircraft for maximum lift, would then sweep back to optimize performance as the plane launched into the sky. Challenges and innovations in wing design. The F-14's wings were a true feat of aerodynamic engineering. The swing wings not only provided flexibility in flight, but also allowed the aircraft to handle a variety of challenges. At higher speeds, the wing would shift backward, and this would cause the aircraft's center of lift to shift as well, which could cause the nose to dip. To counteract this, engineers installed extendable vanes on the leading edges of the wing to generate additional lift and keep the aircraft balanced. The aircraft's wings were also equipped with spoilers and a horizontal stabilizer known as the taileron to control roll and pitch. The taileron was constructed using boron fiber composites, a lightweight yet strong material that helped reduce the weight of the tail section. These innovations allowed the F-14 to perform well under extreme aerodynamic conditions, including high-speed turns at Mach 2. The F-14's legacy and retirement. Despite its incredible engineering, the F-14's service life was relatively short. With the collapse of the Soviet Union and the advancement of newer multi-role aircraft like the F-35, the US Navy could no longer justify the expense of maintaining such a specialized fighter. The F-14 was retired in 2006 after 32 years of service, but its legacy remains as one of the most advanced and iconic aircraft ever built. The F-14 Tomcat was a masterpiece of aviation engineering designed to perform a specific task with precision and power. Its variable sweep wings, titanium wing box, advanced radar, and powerful engines made it a force to be reckoned with. While it may no longer be in service, the F-14 will always be remembered for its incredible design and its place in the history of naval aviation. And that's a wrap on our deep dive into the incredible engineering of the F-14 Tomcat. If you enjoyed learning about this engineering marvel, make sure to give this video a thumbs up and hit that subscribe button to stay updated on more fascinating aviation stories. Thanks for watching, and we'll see you in the next one.